Okay, this is a review of address translation with paging from logical address to physical address, and a little bit more about paging and how the addresses are generated. And so let's get started. All right, so I have two diagrams here. The first one is a virtual representation of P1. So this is P1, and P1 has been represented by my system in a contiguous way. So these are all the instructions that make up P1, and this is the logical representation or virtual address of P1. Now this diagram on the right represents physical memory, and this is my real physical memory. It's just a portion of my physical memory that has been broken up into equal size pieces called frames, and P1 has been broken up into equal size pieces called pages. So what happens in a system is that you have this the information that you need in order to use the information or run instructions or use the data. The information must be loaded into memory. But in a paging scheme in virtual memory, all these pages are not put into memory. There's different ways it can be done. It can be done by demand paging or by anticipating or anticipatory paging. But no matter how that is done, the pages must be put into frames in memory. The pages are the same size as the frames. The instructions and the data are on the pages. So say, for example, your system needed something right here that's on page 3, located right here on page 3. Well, you can see that it's located on page 3, but it's not at the beginning of page 3. It's somewhere within the page. So your system will generate what's called a logical address. And that logical address will be made up of two parts. The first part would be the page number. So this P right here stands for the page number. And that's very clear here that it is in this situation, it's page 3. But the other part of the address is made up of the offset, or D for displacement. And what that means is because it didn't start at the beginning of the page, that's the location from the beginning to right here where the actual information is located on the page. So this is called a logical address. It's made up of a page number, and the number of bits that are used for the page number indicates how many pages there are. And the number of bits, let's get another color here so I can write that. The number of bits that are used for the page number, so that indicates the number of pages. And in this case, there's 12 pages, so you would need 4 bits for that. And the displacement, or the offset within the number of bits used for that, is the size of the page. So you could just say our pages are 32 bytes, just to make things simple. So if our pages were 32 bytes, then you would need 5 bits for your 32 byte pages. And I'm going to show a little bit more of that in the next slide. All right, so this page, which is page 3, now the operating system or your memory manager says, okay, you need something on page 3, but we need to put that page into a frame first. So let's color in our page 3 here. So this is page 3. And we do have a logical address of what we need. So the system's going to say, oh, well, let's look and see if we can find a free frame. So let's just say that frame number, we don't want to use 3, use something different. So frame number, for some reason I can't, there we go. So we got frame number 7 is available. So we take page 3 and we put it into frame 7. And so page 3 is now in frame 7, and what we need is actually at the offset within the frame, which is right here. So this is going to generate a physical address. And the physical address is going to be made up of the frame number, which in this case is frame 7. And if I have 16 frames available, I'm going to need 4 bits for that as well. But that's if there were more frames, then then it would be different, but they just happen to be similar in size. And over here, this is the displacement or the offset within the frame. So this is going to be the size of the frame, and this is going to be the frame number. And this is the actual physical address. And the offset is going to be the same. Like the offset, as you can see, if you start here at the beginning, well, maybe my diagram's a little off here, my drawing, but you assume that the offset, which is the location within the frame, which was the same location that was on the page. All right, so this is just an explanation of what I just talked about. You have here, this is the virtual address or logical address right here, which is split up between the page number and the offset within the page. So just to remember, this is the size of the page, and the offset, this is the size of the frame, and the offset is going to match. They're going to be the same. If this is, if you're talking about the same instructions, that's the same page that's put into that frame, the offset is going to match. Over here, this is the page number. So this is the number of pages. So in this situation, we have 13 pages. So over here, the page number, it's going to be 0 through 12. Okay, and this is the size of the page, which I said in my example that I have 32 byte size pages. So that would mean that the offset is going to be somewhere between 0 and 31. And here is my frame. So this is the number of frames, which in this particular example, we have 16 frames. So the frame number is going to be between 0 and 16, and the offset is going to be between 0 and 31. So let's just say, for example, the offset is 0, 0, 0, 1, 0, 1, 2, 3, 4, 5. Then this would be the same, 0, 0, 0, 1, 0. But the page number would be different because this was page 3. I think I said it was page 3. This was page 3 and frame 7. But the offset would always be the same. All right, so let's talk about how these virtual addresses are generated. So let's just say, for example, that you had 20 bits of virtual address space. So you could take that 20 bits of virtual address space, which is 1 megabyte, and you could break it into page number and offset within the page. All right, so let's say we took it and we broke it up into page number and offset with the page, and we used 10 bits for the offset and 10 bits for the page number. So what does that mean? That means that you would have approximately 1,000 pages, all size 1 kilobyte. If we took the same 20-bit virtual address space and we broke it up into, oops, I'm in the wrong spot here, and we broke it up into, say we have 13 bits for the page number, so that would raise the size of our pages from 1 kilobyte size to 8 kilobytes. So we have 8 kilobyte size pages, and we have 7 bits for our page number. That would give us approximately 128 pages. So you can see how if you make your pages larger, you would have less pages, and if you make your pages smaller, you would have more pages. So let's just say, for example, that we have a 1 megabyte of virtual address space, and we're mapping to 8 megabytes of physical address. All right, so we're going to use 23 bits for 8 megabytes, and we're going to break it up into frame number and displacement within the frame. So if we have this situation right here, we would have 10 bits for our frame. So we'd have 1 kilobyte size frames because the size of the page needs to match the size of the frame, but we would have 13 bits for the frame number, so we would have approximately 8,000 frames, all of size 1 kilobyte each. And if we went here and used this size, we would use 13 bits for our frame, which we'd have 8 kilobyte size frames and 10 bits for the frame number, and so then we would have approximately 1,000 frames, all of size 8 kilobytes each. So the thing to remember is that this side of the address is the size of the frame and the page. And this side of the address indicates the number of frames or the number of pages. All right, so let's do a little exercise here. Here we have 2 processes, and these processes need to go into memory. So this is my physical memory, and these are 2 processes. So this process has 8 pages, and this one has 9 pages, and these pages all need to be mapped into physical memory. So let's say, for example, I needed something right here on page 4. Okay, so this would generate a logical address that's broken up like this, and it would be page number 4, and it would be offset within the page. So if I have this could also be represented like this, which would be page number 4. And let's just say, for example, we'll keep like we had before, that we have 32 byte sized pages, so that I would need 5 bits for that. So this would be the offset 1 0 1 0 1 1 2 3 4 5. Okay, so we take this page 4, all this, I'm just going to keep it blue to make it easier, and we find a free frame list. So we find a free frame list right here, and we can put it into frame number 2. So page 4 is now in frame number 2. Then an entry goes into our page table that says that page number 4 is now in frame 2. So this would then generate and add a physical address for this, where we would have page 2, and the offset within the page is going to be the same. So it's located here. So that would be the physical address that's generated by this, and this would be the logical address of that. And if we had multiple processes that are being mapped into memory, I just put a different process here just to indicate that process 1 is all broken up into equal size pieces called pages. Process 2 has the same size pages, but this is the virtual representation of process 1, and this is the virtual representation of process 2, and this is the physical memory that could be shared. So for example, process 2, let's pick a different color for process 2, like red. So say we needed something that's on page 1, like this offset up here. So this would generate a logical address here. That represents the page number, and then let's just say that offset is right there, and we need to find a free frame. So let's say we found frame 5 is free. So then it shows that page 1 is in frame 5, and then that would generate a physical address made up of the same offset, only this would be frame 5. So I hope that helps, and I'm going to move on and just do this quick exercise similar to your homework. So here's this was one thing that I've already covered in another video. Maybe we could just quickly pick a letter. So I'm just going to pick the letter F. So let's pick the letter F here. So the logical address for the letter F is on this page at this offset. So the logical address for the letter F is going to be on page 1, offset 1. And then if we take a look here, that page F, this data F has already been put into a frame, and that's frame 6. So the physical address of that is going to be frame 6, and the offset is going to be the same. Oops, I drew a line under the wrong one. Okay, that's the offset. So you could pick any letter here. Let's pick one more letter. We'll pick the letter N. The letter N is on page 3 with an offset of 1. And the letter N here is in frame 2 with an offset of 1. So that's the letter F, that's the letter N, that's the letter F, and that's the letter N. All right, so the next exercise I want to show you is this little exercise, which I've already done, but I'm going to do it again. So let's say that you have a 32-bit virtual address. So if you have a 32-bit virtual address, that means that it's broken up into page number and offset within the page. And if the size of the pages are 4 kilobytes, that means that you need 12 bits for 4 kilobytes. So that means that your virtual address is going to be split up with 12 bits for the offset, and if it's 32 bits, that leaves you 20 bits for the page. So that means that you can have 2 to the 20 number of pages, all of size 2 to the 12 size. And it also means that in your physical memory, since the size of the pages is 12, the size of the frames is going to be the same, 2 to the 12 size frames, but you only have 128 megabytes of physical memory, so that would mean that you need 15, you can use 15 bits, or you would have 2 to the 15 number of frames. So how many frames does the system contain? 2 to the 15. And if we go back here and see what 2 to the 15 is, 2 to the 15 is approximately 32,000 frames. So you'd have approximately 2 to the 15, that should be a 2 to the 15, it's a little messy, or approximately 32,000 frames. The next question says, how many bits are used for displacement? 12. How many bits are used for the page number? 20. And this is an extra question. How many bits are used for the frame number? 15. And if this is a virtual address, you have to recognize that you are using 12 bits for the offset or displacement. So that's 4, 8, 12. So the line needs to be drawn here. So this is the offset, and this side indicates, these 20 bits right here indicates the page number. So this would be page number 5. So page number 5 happens to be in frame number 2 and it's valid. So we have the address here. If I draw a line at the same location here, you can see that this is frame number 2 and the offset matches. So I hope that helps you to understand a little bit more about paging and address translation.